In this video, I'm going to briefly look at dangers of radiation, and I'm also going to look at the uses of radiation. And this is mainly aimed at teachers who are teaching GCSE radiation. So in terms of dangers, it's really important that students can distinguish between irradiation and contamination. This comes up almost every year on an exam paper in some form, and students, for some reason, are not always confident on the differences. So irradiation is where you are exposed to radiation, but then the radiation is removed. Okay, contamination is when the radiation basically, or the radioactive, I should say, radioactive material stays on you. Okay, so it's actually on your clothes or you've breathed it in. And it should be fairly obvious that contamination is obviously far worse than the radiation, because you're going to get a much higher dose for a much longer period of time when you're contaminated rather than just irradiated. Students also need to have some idea of sort of relative levels of dose. So you should look at lots of different examples, either through exam questions or there's a really nice Veritasium video. So the channel is Veritasium. I'll try and remember to link to it in the comments. And it's called What is the Most Radioactive Place? Or something similar to this. What is the most radioactive place on Earth? And he visits Chernobyl, he visits some other radioactive places, and he talks about the relative levels of radiation, and then he concludes that certain careers, such as being an astronaut or a pilot, expose you to far more radiation than you might realize. And if you're a smoker, you have an even higher level of radiation dose each year, because there are lots of radioactive chemicals in cigarettes. So this is a must-watch video, and I usually play it in full to classes. So they really love it, and it really, I think, makes it clear as well. It also, in this video, talks about the banana scale for radiation dose. And this actually came up on an exam a year or two ago, where it was like, why are bananas used as an equivalent dose of radiation? And you had to say, it's a very memorable, easy to understand thing, and understand scale. You can make comparisons really easy, and it's much easier than trying to give the general public information in terms of actual scientific units. So the unit of kind of radioactive dose, or I guess exposure, we tend to use sieverts SV. Now, this is not a super simple unit. It depends on a few different things. Students don't need to know this for GCSEs, it's worth mentioning, but something like the banana scale is far easier to understand. So in summary, watch this video. Students should also be aware of kind of safety measures when handling radiation, or when radiation is around, and we would link this to the practical, or not the practical, the demonstration that I'll show you in another video, where you actually get out the sources of radiation. But in summary, safety measures, for teachers handling radiation, you need to keep the exposure time as short as possible. Fairly obvious. Use tongs to handle it, because then that obviously reduces the risk of contamination. Gloves, I wouldn't write down gloves because we don't really use them, and if you're using tongs, that kind of reduces the need. You could potentially say breathing equipment, for example, or wear safety overalls, like you'd see in a film where the radiation officers swoop in. But again, we don't do that in class, so I think it's less useful. We want to kind of prioritize these two. The other obvious one as well is keep as far away from it as possible, which in class, when we're doing the practical, is obviously reflected by the fact that the students, sit relatively far back, a couple of meters back. And then also, this one is always a little bit odd, but don't point radioactive sources at people. Now, this is a little bit odd because if you have some radioactive source, then it could well be emitting in every direction. But this is certainly given as a safety precaution when you're doing the demonstration. I think that's because there's a holder that actually blocks most of the radiation out. So the radioactive material's in there, and most of it only actually comes out through the kind of thin hole in the front. So that is obviously the much higher danger than anywhere else. Now let's look at some uses. There are quite a few uses. It's hard to really give a definitive list because they could come up with a few different scenarios, but the main ones I will talk about here. So for alpha radiation, we've got smoke alarms. So not heat alarms, but smoke alarms. So you have in a smoke alarm, you have a circuit, and you have a radioactive source. And the radioactive source ionizes the air. And because it ionizes the air, we can get a current. So the alpha source ionizes the air. Current can flow. Okay, when smoke comes in, it gets into the chamber here, right? So smoke enters the chamber, and then we know that alpha has a very short range in air and is blocked very easily, so the smoke absorbs the radiation, and then it stops the current flowing, and then the alarm goes off. Okay, so it's quite simple and a nice demonstration that radiation isn't always dangerous, because almost every person's house will have one of these sources inside. But obviously, you would never go and open the smoke alarm unless you're changing the battery, because you don't want to, expose yourself, either irradiate yourself or contaminate yourself. The next thing we'll look at, let's look at beta. So beta decay can be used for thickness control of aluminium or just metal in general. So you will have in your factory, you will have your production line where metal is being moved along between some rollers. And these rollers can move in and out to change the thickness of the metal. And then you'll have yourself a radioactive source. And that will be firing radiation through the metal. And then you'll have a detector. Okay, so if the metal is too thick, then what happens? You get all the radiation is absorbed. And if it's too thin, then the detector detects a higher count rate, more radiation particles per second, and therefore there are instructions to the rollers to change the thickness. Now, it's very simple. You probably want to explain it in slightly more words than I've explained here, but the concept is very simple. The only thing that's maybe worth mentioning is that aluminium is the main one, but sometimes paper might also come up in a question as well. The next one that we'll look at is tracers. So tracers typically are medical tracers, but there is another sort of form of tracers in a second. So here's my person. All right. What do? They ingest in some way. They drink or they eat some radiation. Okay, the radiation travels down inside their body and pools in some organ. Now, depending on the organ that you're trying to image, you'll take a different type of radiation. So if it's your thyroid, you might take something with iodine in. If it's your lungs, you'll take something else. If it's your liver, etc., you'll take a different type of substance. And that is obviously linked to the biological processes of what organ does what and what organ takes in certain chemicals. But the radiation pools in an organ or builds up, and then it emits radiation, and that's detected, and then we can build up a really high quality image of the organ. So the radiation is detected, and we can build up an image of that organ. Okay, so these are used all the time in hospitals to image different parts of the body, and you can find loads of really good high quality images on the internet for this. Now, tracers may also be used in the context of pipes. And they can be used in two ways, really. They can be used to detect blockages or find leaks. So again, we inject some radioactive material into the water or the pipe or the oil or whatever it is, and it will travel along. And then if there's a blockage blocking the pipe, okay, the radiation will build up here. Okay, or if there was a leak in the pipe here, the radiation would get out into the surrounding area. And then above ground, you have a person with a detector, and they are going to be detecting the radiation either from the leak where it's built up, or you'll notice there's obviously a lot of radiation before the blockage and nothing after the blockage at all. The type of radiation used for this, right, because obviously we need to travel through a large amount of ground or the whole of your body, is going to be gamma. There is a related type of medical use that's to do with beta. So this is PET scans or positron emission tomography. And this is where you use positrons, which are beta plus particles. These positrons, these annihilate with electrons. So what that means is we have a positron plus an electron. They meet and then they destroy each other and turn into two gamma rays. And those two gamma rays, because of the conservation of momentum, will travel in opposite directions. So here's our patient lying down. The two gamma rays will travel in equal and opposite directions, and then they can be detected by a detector. And this is another way of imaging inside the body. and is used in certain, for certain organs that, depending on obviously the chemistry and the biological processes, to build up really good images. And again, you can search on the internet for these as well. Finally, another use for gamma is sterilizing medical equipment or food. All right, so the gamma radiation will destroy any bacteria or viruses that are on the medical equipment or food and make it safe to be used, again, in hospitals, or to prolong the life of food. And again, there's some good images on the internet of food that has been sterilized compared to food that hasn't been sterilized, and you'll see that the food that has a much longer shelf life. And actually, a lot of fruit and vegetables in our shops have been treated with gamma radiation. Why does this work? This links to basically dangers and uses. And this is basically a stock answer that students need to learn. Okay, radiation is ionizing. It damages cells and can lead to cancer. All right, DNA is even better than cells, but that's fine. So radiation is ionizing, it damages cells or it damages DNA and can lead to cancer. That's basically a stock answer. Probably the last thing to say that links to dangers and uses links back to the properties of alpha, beta, and gamma. So alpha is highly ionizing, beta is sort of medium ionizing, and gamma is low ionizing. So in terms of when it's inside the body, what is the relative danger? So alpha is stopped by skin. So inside the body, it can't escape. So it's highly dangerous. And this might be a good time, if you haven't already, to bring up the murder of Alexander Litvinenko, the Russian spy who was killed by polonium in his tea, which emitted alpha radiation. And within, I think, a week, he was dead with absolutely nothing that could be done because they just couldn't get the alpha radiation out of him. Beta radiation, it's stopped by metal. It will go a few meters in air. So this is kind of, medium danger, right? It mostly can escape the body. And then gamma radiation is generally the lowest danger because it will almost all leave the body without doing anything, right? It can easily escape the body. Now, what does that mean for radiation outside the body? So outside the body, this is the lowest danger, all right, because it can't penetrate skin. Beta, again, medium danger because some of it will actually get in the body. And gamma is generally the highest danger because it's penetrating. It can get inside the body very easily. Students might ask you, what does radiation damage look like? So, although this is kind of the standard exam question answer, what are the effects of it? Well, if you've ingested something like alpha radiation, your organs start to fail, you feel sick, your hair falls out, and then your whole body stops working. If you get a radiation burn from outside the body, so for example, you've been treated by radiotherapy, you might find that outside the body it looks a bit like sunburn, where actually you've started to ionize and damage the cells on the outside of your body, and so your body reacts by looking a bit red, being a bit sore. which actually reminds me there was one final use for gamma, which is, of course, radiotherapy. Okay, so radiotherapy. And that is obviously treating cancer. All right, so you have your patient, you zap them with a load of gamma rays, and you destroy the cancer cells by hopefully highly targeting and highly focusing the gamma rays on. There is obviously more to an answer than this, but that is a very brief outline to it.